Math 3 Lesson Summary Video, High Noon and Sunset Shadows. This lesson is a develop understanding task, which is meant to introduce you to a concept, but not necessarily finalize rules or strategies. The purpose of this lesson is to introduce the horizontal shift of trigonometric functions in terms of a modeling context. Recall, Carlos has been riding a Ferris wheel with a radius of 25 feet, and the center of the Ferris wheel is 30 feet above the ground. The Ferris wheel makes one complete rotation counterclockwise every 20 seconds. You may remember from previous lessons that the equation for the height of the rider on the Ferris wheel above the ground was determined to be h of t equals 25 times the sine of 18t plus 30. Remember, this was our amplitude, and it was the radius of the circle. That's how high up and how far down we're going. The 30 was the actual center of the Ferris wheel. The center of the Ferris wheel was 30 feet above the ground, and so we had our center here, and we said for the graph, this was the midline. And this number on the inside here, it gave us our angular speed. Because we know sine and cosine always has to be an angle in here. In order for us to figure out how many degrees we have turned, we have to take our angular speed and multiply it times our time. And so we had to figure out our angular speed. And since it takes 20 seconds to do one full revolution, that was 360 degrees in 20 seconds, which was 18 degrees per second. And you may recall that the graph looked something like this. We had our midline. We were starting there on the right side in the middle, and we would go up, and then we would come back down, and then we would come back up, and we're back to where we started. And it gave us that nice periodic graph. You may also recall that we found for the shadow on the ground, as we went left to right, as we're going around the Ferris wheel, we found the equation for that horizontal distance from the center to be d of t is equal to 25 times the cosine of 18t. Here we said that 25 was again the radius of the Ferris wheel, and it was also the amplitude of the graph. Again, 18 is our angular speed. And we didn't have a midline other than 0, because here the center of the Ferris wheel was 0. If we were on the left of the center, we were negative distance, and if we were on the right of the center, we were a positive distance. So we do still have that center out there. It just happens to be 0. So these were all things that we had established beforehand as Carlos rode the Ferris wheel. So based on your previous work, you probably wrote these equations in terms of the angle of rotation being measured in degrees. Revise your equations so that the angle of rotation is measured in radians. Will it change our graph if we're measuring, or change our equation if we're measuring in radians instead of degrees? The Ferris wheel is still going to have a radius of 25 feet, and its center is still going to be 30 feet off of the ground. We're not physically changing the Ferris wheel. So does that affect the equation? If you think about our two equations, the only thing that is even affected by angles was the input of sine and cosine. What we input into sine and cosine always has to be an angle. And so that's why we had to include that angular speed, because we were converting the time into how many degrees had time passed. So it's that 18 in our equations that are going to have to change. It was 18 degrees per second because our time was in seconds. 18 degrees per second. So we need to change our angular speed to be in radians per second. That's what we need to change for our equations. So before we had said that it was 360 degrees in 20 seconds, because that was how long it took to do one full rotation. So if we don't want to use degrees and we want to use radians, one full rotation is 2 pi in 20 seconds. So 2 pi over 20 reduces to pi over 10 radians per second. So when I write my equation for the first one, I'm going to have that h of t is equal to, the 25 doesn't change, it's the same radius of sine, but instead of being 18t, I'm going to have pi over 10t plus 30. Again, our height above the ground didn't change. When we change the second one, that distance left and right, d of t is still going to be 25 times the cosine. It's just that our angular speed is now going to be pi over 10t. And so the equations didn't change that much. We just needed to change the angular speed. Revise the equations from question 3 so that the writer's initial position at t equals 0 is at the top of the wheel. Now, if you recall our Ferris wheel, we had our Ferris wheel, and for all of our computations, we've been starting over here at the right side, exactly halfway. So we've been starting where we are 30 feet above the ground. That's where we're starting, 30 feet above the ground, and we are 25 feet all the way to the right. So we're always starting 25 feet over here to the right and 30 feet at the ground because we've been starting on this side of the Ferris wheel. They want us to change our equation so that the start isn't here anymore. The start is actually up at the top. So we're going to have to think about that for a second. If I think about what I'm changing, I'm not changing the radius of the circle. It's still going to have a radius of 25 feet. So that part's not changing. I'm still going to be 30 feet above the ground. That part's not changing. Even my angular speed, I'm still going pi over 10 radians per second. I'm not changing the speed of my circle. So all of those numbers in my equation currently are staying exactly the same. So we really need to think about what's changing. All functions have an input and an output. So our original equation for this one is 25 times the sine of pi over 10 times t plus 30. Our input is the time in seconds. And initially, when we were starting over here, if our time was 0, the output was 30 feet above the ground, because this would turn out to be 0, and 0 times anything is 0, and we're adding 30 to it. But now I want my t to be 0, but I want my output to be what the output was here. See, here we were 30 feet above the ground. Up here we were 55 feet above the ground. So here is where I need my output to be. In order for this to be 55, I'm going to have to multiply 25 times 1 instead of 0. Because 1 times 25 would be 25, and 25 plus 30 would be that 55. So the angle that has a sine of 0 is 0. Remember, this here has a sine of 0. Up here at this angle, the sine of this angle, 90 degrees, is 1. So I want my input to be 0, but I want it to have the output of 90 degrees. Or in this case, how many seconds did it take to get up to this point? This was, we said it takes 20 seconds to go all the way around. This is the 5-second mark. So I want its input to be 0, but I want its output to be what we were getting at the 5-second mark. So what I could do is change the number that I'm actually going to take the sine of. if I plug in 0 for my time, my starting time, that's great. That's just not the number I want to take sine of. I want to take the sine of the 5-second mark. So I'm going to add 5 to it. So my input number will be 0, but what I actually take sine of is going to be 5 seconds, which is going to give me that same output that I had at 5 seconds before. Let's try that with our cosine. It's the same thing. If I'm starting at the top, my distance to the left or right is no longer going to be 25. It's going to be 0 because we're right here at the middle, which was the 0 left and right feet. And so again, I want my input to be 0. I want to plug in 0, but I don't want to take the cosine of 0 because I want to end up with the cosine for this spot. That's going to give me this output, and it too is 5 seconds later than we were before. So I want to plug in 0, but I want to get the output that 5 seconds had. And so we're really shifting that graph over. If we remember our initial graphs, sine initially went this way, and we started here at 0. But we want to take this point that's up here at the top of the wheel, and we want to shift it over until it's at 0. We want to make that the starting point. And if you remember from your transformations, if you want to shift a graph to the left, you have to add inside the function. And so all we're doing here is making a transformation. That's what's happening. Revise your equations from question 3 so that the writer's initial position at t equals 0 is halfway between the furthest point to the right on the wheel and the top of the wheel. So if we're thinking about our Ferris wheel, we don't want to be at the point furthest right, and we don't want to be at the point furthest top, but we want to be halfway in between it. So that would be right here. So we're trying to get to shift so that we want our starting point to be halfway between that furthest to the right and that furthest to the top. Time-wise, how long would it take us if we were starting here to get there? We knew that it took 5 seconds for us to get all the way to the top, and that's halfway. So this would be at the 2.5 second mark. So we're trying to get the output that was at that 2.5 second mark to be the output for t equals 0. So again, we're not changing the Ferris wheel. It still has a radius of 25 feet. It's still 30 feet off of the ground at the center. So all we're messing with is what is the output going to be for that input. So it's still going to be 25 sine pi over 10 because our angular speed hasn't changed. And it's still going to be 30 feet above the center. But when I input 0, I want my output to be the output that was at 2.5 seconds. So I'm going to add that 2.5 seconds so that that's the output that comes out. Again, we're shifting that graph left 2.5 seconds. When we do it with our cosine graph, it will also be shifted by 2.5 seconds. Revise your equations from question 3 so that the wheel rotates twice as fast. Okay, so if it's going to rotate twice as fast, I'm changing its speed. So initially, it could do a complete turn in 20 seconds. But if I'm going to go twice as fast, 2 times as fast, that means instead of finishing a complete circle in 20 seconds, I'm going to finish a complete circle in 10 seconds. And so that's changing my angular speed. Now again, I'm not changing the radius of my circle, and I'm not changing how high it is above the ground, but I am changing that angular speed. How fast is it going? If it's doing a complete circle in 10 seconds, that means that we're finishing 2 pi, a full rotation, in 10 seconds. That's going to be an angular speed of pi over 5 radians per second. So when I write my equation, the height above the ground is still going to be 25 for its amplitude because our radius is still 25. It's going to be sine, but our rate of change, that angular speed, is no longer pi over 10. It's going to be pi over 5. Now this time, we still are starting at that far right side of the circle, so I don't need to worry about shifting where it's starting, and it's still 30 feet above the ground. For cosine, still has a radius of 25, but our angular speed is pi over 5 instead of pi over 10. Revise your equations from question 3 so that the radius of the wheel is twice as large. So instead of having a radius of 25 feet, it's going to have a radius of 50 feet. And the center of the wheel is twice as high. So instead of being 30 feet off of the ground, it's going to be 60 feet off of the ground. So if we think about our equations, we did change our radius. So instead of 25, it should be 50. We did not mess with our angular speed though. So that's still going to be pi over 10. And we're not changing where we're starting from. We're going to start at the right-hand side, so that's not getting shifted any. It'll just be the time. But instead of being 30 feet above the ground, I am 60 feet above the ground. For our cosine, we changed our radius, and it's going to be cosine of pi over 10. But it's still left and right from the center at 0, so we don't have a center at 60. Its center is still at 0, so we don't have to add anything to it here.